Hey everybody, and welcome back. Or if it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And what I'm doing on this video is to really continue going through BGP, or Border Gateway Protocol. I've already done 2 videos on this protocol itself. If you haven't seen those videos, if you don't know what BGP is, highly recommend that you check those videos out. Here's one of the links, or just check out the description box. The links are there. Promise you, they're informative videos that you will absolutely love if you're into technology as much as what I am. But on this video, what we're going to be covering is 3 areas which really don't take a long time to actually configure on Juniper Junos devices, but they are absolutely nonetheless absolutely important to BGP and device security itself. Now specifically what we're going to start with is something called GTSM. That is the generalized TTL, or time to live security mechanism. You gotta love it when you have 2 acronyms in one. GTSM, generalized TTL security mechanism. We're going to go through what is this GTSM and how does it actually protect our BGP adjacency, our neighbors, from some kind of spoofing attack where you've got some kind of hacker, some kind of malicious intent, and someone's wanted to get BGP relationship to your router. That's where GTSM actually comes into it. And then when we've got that adjacency, we then need to protect our database, don't we? I almost call it link state database there. I've been doing a lot of content on OSPF, completely different topic. But in both protocols, we actually need to protect that database. In BGP specifically, we need to protect that BGP database, because at the time I'm doing this video, there is over 800,000 routes available in the global internet routing table. Do you want all of those routes to be downloaded as such, to be shared via those update messages from one router to the other router to your router? Maybe you do. Maybe your router will be able to handle that, but maybe it won't. And that's why we're going to go into how to actually protect your BGP database on your router. And then right at the end, we're going to go through something called dynamic neighbor discovery. Now it's a bit of a misleading word, that dynamic. It's not dynamic in the aspect of these iBGPs, which will just send out a multicast packet, and any router that is speaking the same protocol out there and is configured for it will just respond to those. It's not dynamic in that aspect, but I don't want to take too much away too soon. So let's just jump straight on the lap and let's go through GTSM, the BGP protection on the database, and the dynamic neighbor discovery. And so here's the lab that I'm going to be using for this video. It's exactly the same lab that I've used for the previous 2 videos. And what you can see in terms of high level is we've got 2 different enterprises. We've got enterprise here in autonomous system number, or ASN 65100, and over on the right hand side we've got enterprise B in ASN autonomous system number 65200. We've got 3 service providers, 3 ISPs in between enterprise A and enterprise B. We've got ISP1 here, ISP2 here, and ISP3 actually here. In terms of configuration, a lot of the basic stuff has already been done. Again, if you haven't seen those videos where I start building the eBGP peering and an iBGP peering, just check out the links in the description box. But what I have done from a high level point of view is I've configured the eBGP peering between all the different autonomous system numbers, as well as iBGP peering inside the autonomous systems themselves. Now, if you've seen the other videos, you might recall that I've got OSPF and ISIS running as the underlay interior gateway protocol. So I've got OSPF running in this network here. I've got ISIS running in ISP1, and I've got OSPF running in all the other networks. Guess what protocol I'm a fan of? I much prefer OSPF to ISIS. Don't ask me why. Honestly, I don't know. I just prefer it. I've had more experience with it. But obviously, we're not here to talk about OSPF. What we are here to talk about is, first and foremost, the GTSM, the Generalized TTL Security Mechanism. Now, we're not going to do the configuration on all these routers because you're going to get bored. I'm going to get bored. So we're only going to do it on the one. Now really the focus on this video is really these routers here. So that is router R19 and R17. So let's just focus in a little bit more on these two routers. And so here's the routers of interest for this whole video. We've got routers R19 and R17. Now what is GTSM? Let's first look at the concept of why we need it in the first place. Now, as I just said, the eBGP peering has been built between these different autonomous systems. That's fine, that's great. Now, in the Junos world, you do that by configuring in a specific group the neighbor address. So on both routers, what they'll do is they'll actually define, well, what is the neighbor address of this router over here? What is the neighbor address of this router over here in terms of their actual interfaces? And then if everything is configured correctly and the ports are open, etc., they'll basically establish that eBGP peering, adjacency to and from each other, absolutely no problems. But here's the catch. You can, especially in enterprises and in service providers, you can have a malicious, and I'm just going to draw a bad dude here. Actually, that doesn't look like a bad dude, does it? I'm going to have to remove that. There we go. It looks a little bit more sinister now. The previous face I've done looked sad almost. I'm really not an artist. But now we've got a malicious hacker who looks a little bit more malicious. And say this hacker is connected to the service provider network, and obviously there's going to be X amount of routers in here. This is a safe environment, it's virtual, it's on my bare metal server, there's nothing to really worry about here. But just say, for example, this malicious hacker has got access to this router here. Now, I'm not a hacking expert for obvious reasons. It's an area of the telecoms world I've never really wanted to get into. But what I do know is that they can spoof IP addresses. So what the hacker can actually do is spoof, i.e. copy, replicate, take that IP address on the interface itself. Now you can't actually see what it is here. My good old drawing is copying it. It's something like 170.10.20, and I assume that's probably a .22 or .21. Really doesn't matter. But they're basically going to take the IP address that is on that interface and try to get that adjacency to your router. eBGP builds adjacencies on the interface's IP address. iBGP builds the adjacency based on the router's loopback addressing. And without going into NAT, etc., the interface's IP addresses can be easily seen. A general trace route, you can find those IP addresses. So it could be potentially easy for any hacker to spoof an IP address. What is not so easy to spoof though is the TTL, or time to live. When you've got, say, 4 routers connected together, the TTL at this end will be set to 255. And once it goes through to the next router, it's then decremented to 254, decremented to 253, and so on and so forth. So it's not by hop, it's actually based on time, because then that would be a hop count, it's time to live. But basically, if this time to live ever gets to 0, or actually it would be just 1, then those packets would be discarded, because it could inform a router that, that this packet has been around for a while, the time to live has decremented all the way down to 1. I'm not going to forward it anymore because the next one will be 0, so I'm just going to drop it right here. So it is a bit of a loop prevention mechanism. But the TTL is a lot harder, if not impossible, for these malicious hackers out there to actually spoof. So what we need to do on the Junos devices is actually say, if the TTL is not anything except, and I'll come on to that, 255, because these are adjacent routers to each other, I'm just going to drop that packet. Because this hacker is more than likely connected quite a few routers away from your router, by the time those packets get to wherever they are actually located to your actual router, that TTL is no longer 255. It could be 240, 100, doesn't actually matter. But that's why the GTSM, or generalized TTL security mechanism, was created and adopted onto the BGP protocol, because we're saying if the TTL is anything lower than what I'm configured to actually accept, I am just going to drop that packet. So it's a way to protect your router from forming adjacencies from any malicious attackers out there. And the configuration to configure GTSM on Junos is incredibly straightforward. You need to take it as a two-step process. One, you need to configure a firewall filter which will define if I don't receive anything then this particular TTL value, whatever that may be, then I'm going to discard that packet and then accept everything else. But also you need to configure the adjacent router to send those BGP packets with that specific TTL value. So it's a two-step process, it has to be done on both adjacent routers. So first let's log on to R19, which is this router over here. And this is where I actually want to configure the GTSM because this is Enterprise B. This is ASN 65200 and we actually have our ISP3 here in ASN 3 for obvious reasons. Which is going to provide the services and the connectivity to the actual internet. So for me, it makes sense. You probably want to do this both ways, of course, but it makes sense just in this lab to actually do it on the enterprise router itself. So I've logged on to R19, gone into configure mode, and the first thing we need to do is to define that firewall filter. So let's go edit, firewall, filter, and I'm going to call it GTSM for obvious reasons. And you can immediately see we've just created the firewall filter, but obviously there's no contents actually in there. So first we need to define a term. So I'm going to say set term 1, never forget the spacebar. And now you need to say, where do you want to receive these packets from? What do you want to either accept, discard, reject, police, whatever it actually is you want to do. Now I need to define a source address. Now that source address is of the adjacent interfaces themselves. So you can see here, and we've got two connections, which is why I chose this router or routers, is we've got 170.10.20.18 and 170.10.20.22. So I'm going to say 170.10.20.22. And you don't have to do the /32 because if I now do show, you can actually see it's already populated that as an actual host address, i.e. the /32. But additionally, we do need to say a little bit more than just the source address. So I also need to say from protocol TCP because BGP uses transmission control protocol. It is a stateful protocol. We also then need to define the port. Now BGP, if you saw the other videos, you know that it uses or does use port 179. And if I just do a quick show, you can see it's starting to expand a little bit more now. So we're saying from term 1, from source address 170.10.20.22, if it's using protocol TCP, and if it's from port 179, then I want to take a particular action. But there's one more thing that we actually need to do, isn't there? We need to say what the TTL is, or time to live, that we actually want to look for. So here, if I just do question mark actually, and go all the way to the bottom, you can see we've got TTL. So we need to match the IP TTL type. Now you would probably think this is the one that we actually need to use, i.e. TTL. It's not, because here we are matching the exact TTL type, i.e. the value itself. We need to do TTL accept because don't forget that TTL is going to decrement by 1. So what we need to do is say TTL accept, and now I give the actual value itself. So I'm going to say if the TTL is anything lower than 225, i.e. it's anything except 255, because these are adjacent routers, then I want to discard them. If I'd have done TTL 254, 253, it's looking for that specific TTL value itself. Whereas we need to say accept, anything except this value, take this action. And now if I just do set term 1, then discard and do a quick show, you can now see we've got a very nice looking firewall filter, haven't we? But don't forget there is actually two interfaces. There are two connections to and from R19 and R17. So I also need to say set term 1 source from source address 170.10.20.18. Again, I don't have to worry about the /32 because Junos, being wonderful, has already done it for me. Now with firewall filters, there is just a deny all at the end. So here we're saying term 1, just discard these packets, but after this there would then be another discard policy which is just hidden. So we do need to say then set term 2 then accept. So then all traffic which doesn't match these definitions here will actually be accepted. They won't be blocked, they won't be discarded. Normal traffic will still pass through. So we've got our firewall filter actually defined. It's not working yet because we need to then implement, we need to put that into the interface itself. You might have thought that you need to put that into BGP. No, that's where you define routing policies and where you import or export those routing policies into that protocol itself. Firewall policies, filters, are done on interfaces themselves. So we need to just go to the interface, i.e. GIGI001 and GIGI002, and say, I want you to use this firewall policy. So let's go to the top and let's do edit, interfaces, GIGI001, unit 0, family iNet, and just do a quick show. You could see it's just got the address actually configured there. Now if I actually just enter in set here, you can actually now see we've got the set filter for packet filtering, which is exactly what we want to do. So let's do set filter, hit question mark. Now you could say, do you want this in the input direction, i.e. packets that are coming into this router, or do you want to apply it on the output, or do you actually want to chain together different filters? So it's can be quite advanced. But in this case, because these packets are coming into this router, we need to say input itself. And now if I hit question mark after that, you can see there is GTSM. And now if I just do up to, so I'm back on the GIGI001 interface, do show, we can see unit 0 has the firewall filter, GTSM has this address, but that's not committed just yet because I need to do the same on the GIGI002 interface. So I'm just going to do set GIGI002 family iNet filter in the input direction GTSM, and there we go. That's actually there. That's configured. Now if I actually just run the commit command, then that configuration is in place on R19. But don't forget, this is a two-way street. We now need to configure R17 to send, and it will do anyway because this is directly connected, but we need to configure it to explicitly send BGP packets with that TTL value of 255. So let's log on to R17. It's going to the command line interface, into configure mode. Where do you do this? You do this in the protocol itself. So let's go into edit protocols BGP. Let's do a quick show, and you can see I've got my external group which is facing the enterprise B, i.e. external AS 65200, and then I've got the group which is facing service provider number 2, basically, i.e. external autonomous system number 2. What I need to do is define set group external 65200 TTL 255. Now if I do a quick show, you can see there it is right here, and that's it. That's all we have to do on R17 apart from hitting commit, and that is that configuration done. That is how you configure generalized TTL security mechanism on a Juniper Junos device. Yes, it's a two-way street, but this would then prevent any hackers, malicious attackers out there from spoofing an interface's IP address and trying to get adjacency to your router and to maybe flood it with all different types of BGP updates, which wouldn't be a good thing. And that actually leads us on to the next topic, which is how to protect your BGP database. So the next important aspect of this video is how to protect your BGP database. Now this is important whether it be OSPF, ISIS, BGP, more so in the BGP world because we are building connectivities, adjacencies with eBGP to external autonomous systems, to external networks. And as I said on the last part, there are unfortunately malicious attackers out there. Now, the internet itself is filled with network prefixes, with network routes. And as I said at the beginning, at the time of me writing and doing this video, there are over 800,000 routes globally available on the internet. So the global routing table is over this size. Now that is a huge amount of information, because each one of these will have specific attributes. Now that's ranging from local preference to autonomous system path to the origin, so on and so forth. And obviously within that, the network layer reachability information, i.e. who you want to reach in the first place, that network itself, and how do you actually want to get there, or I should say, how could you actually get there. But additionally, when it comes to these 800,000 routes, this is obviously going to impact the device's memory. Regardless of vendor, every device that has computing to it, your Xbox, your Switch, your router, your access points, it has a dedicated certain amount of memory. And if you download, as such is the bad way of putting it, but if you share from one router to another router the global routing table into a router and it doesn't have enough memory, then it's obviously going to be overfilled with all these entries, and that is going to have catastrophic implications on that router itself. It just won't be able to handle it. And that's why they also say you should never import the BGP table into your interior gateway protocol. Whether it be OSPF or ISIS, RIP if you want to go there, it really doesn't matter. They're not built to handle the size of the global internet routing table. BGP is perfectly designed to actually handle that, for lack of better words. So never export BGP into iBGP, but that's a separate topic. However, in this particular topic, what we want to do is harden R19 to only accept a certain amount of routes from its adjacent router, which is R17. So we may only want to configure it to have 100,000 routes. It's only accepting as such an eighth of all the routes that are available on the internet itself. But also you then might want to say, well, I want to define, if it gets to a certain value or certain percentage of this particular number itself, I want the administrator to be alerted to that. I want to tear down an alert at a specific percentage. You could also define things such as idle timeout. So if you tear down a BGP peering because you've exceeded this value here, the idle timeout literally defines, well, how long do you want to wait until the next period where you build the adjacency? Will it be 5 minutes, 10 minutes? Doesn't matter. It's a pause. It's allowing some form of recovery for that router itself. Now, this sounds complicated, but this is incredibly straightforward to configure on Junos devices, and thus protecting your BGP database. So I'm back on router R19, and as you could see, that's the previous configuration we'd done for the firewall filter, i.e. the GTSM. Now, where do we actually go to define how to protect the BGP database? Well, the answer's in the question itself. We have to go to the BGP protocol. So let's go edit protocols BGP. And what I want to do is I want to define a specific prefix limit. Now, what you can do with this prefix limit is you could do it at the BGP level, or you could do so at the group level. I haven't verified, to be honest, if you could do this at the neighbor level. We'll see in just a second, actually. But what you can do is say set BGP, and let's do family. So we want to do family INET because this is using IPv4. And if I hit question mark, you can now see we've got, any. We don't want to be doing that. Multicast, transport. We need to be using unicast because these are unicast packets going to and from different routers. And then if I hit question mark, we can now see right here is the prefix limit itself. This is the command that you will start to use to define a maximum number of prefixes from a peer. So let's do prefix limit, hit question mark, and now we can see all those options that I was literally just describing. So now if I do maximum 100, and I'm just going to do a test here. I'm going to do 100k. Does it accept that? If I do show, and there you go there, actually. It's rounded up to 102,400 for something. It's probably something to do with the power of 2. But I'm going to delete that and just do 100k, just to be a bit more specific. So there we go. There's my set prefix limit maximum 100,000. If I now do show on that, you can now see it's entered in there. So prefix limit maximum 100,000. So what that means is if R19 receives from R17, regardless of interface that these updates come from, if it receives more than 100,000 prefixes from the service provider, from R17, then I want to take some kind of action. Now we haven't defined what that action actually is yet, and that's where the next command comes into it. So now if I do tear down, what this means, and actually if I hit question mark, what Junos says is it's going to clear that peer connection on reaching this limit. So we've said that I want to take a particular action, i.e. if I tear down at a particular percentage, because here we're talking a percentage, so if I'd say 85, that means 85,000 prefixes, 85% of 100,000 is obviously 85,000, then when it reaches that 85% value, I want to tear that connection down itself. So you can actually see here, maximum 100,000, that is the maximum I want to receive, but upon reaching 85% of this maximum, just tear that connection down. However, what you can also do is, as I said, the idle is the idle timeout. So you do have to be in tear down, but here if I do idle timeout and then hit question mark, you could say, well, I want the connection to be always down for forever, never want it to be re-established, or you can enter a particular time. So here I can actually say 10 minutes. So it'd be 10 minutes between the different adjacencies being torn down and rebuilt. Now that is how we actually protect the BGP table. So we've got two groups. We've got external ASN 3 and then internal ASN 65200. So one's running eBGP, one is running iBGP. Now, because I've done this at the BGP level, both groups will inherit this configuration, which is great. But if you wanted your internal, just for example, to have a different value, you could do so at the group level as well. So let's do set group internal family inet prefix unicast prefix limit, and now I'm going to say 20,000 just to be a bit prefix limit maximum 20,000. I'm forgetting a few commands there, and now I can say tear down at 90%, idle timeout 5 minutes. So I've done that deliberately because that is completely different from what I configured at the BGP level for all groups, and you can see at the internal group level it's obviously different. So this is more specific. So group internal ASN 65200 will use this configuration because it's more specific to that group itself. And that is how you actually protect your BGP database. I did say we'll test to see can we do this configuration at the neighbor level. So let's just go into edit group and let's go into external just to be different, and let's do set neighbor, hit question mark, and we got our different neighbors there. So we'll do .18, it really doesn't matter. Hit question mark, do we have family inet? And we do have family, so here we go. So this is looking positive. So family inet unicast, do we have prefix limit? We do. So not only can you do this at the BGP level where all groups inherit that configuration, you can also do it within a particular group where all neighbors within that group will inherit that specific configuration, or you could do it all the way down at the neighbor level, which would be the most specific of them all. So as you can see, Junos is incredibly flexible when it comes to this type of configuration. So this next part of the dynamic neighbor discovery isn't dynamic, as I said at the beginning, i.e. it's not like the IGP protocols where we send out a multicast packet and eventually we'll get a response. What we're doing here with the dynamic neighbor discovery is defining to allow a particular subnet. So the allow command is actually the command that we're going to use within BGP, i.e. allow. And what we're going to do is define a subnet. Now this isn't really realistic for this network here, but if you're in a data center where you've got spines and leaves, and more so on the leaf devices where you're connecting to bare metal servers, maybe some kind of external router, firewalls, and there's virtual machines in those bare metal servers, so on and so forth, they're all going to have different IP addresses, and maybe they need BGP adjacencies. That's just the theory. And in the data center environment, you don't want an operator logging on constantly to tear down a BGP relationship to build another relationship and keep doing that every single time a virtual machine is spun up or moved, so on and so forth. So this allow command is very beneficial in that data center environment. Now this isn't actually going to keep that device secure. This isn't about hardening BGP like the previous two parts of this video, i.e. GTSM and protecting the BGP database. But this is, as I said, how to make that of the operator's life a little bit more easier. So we are actually going to go onto router R19 and define what subnets do we want to allow. Now, it is important to know that you cannot have allow on both R17 and R19. The reason why is because they are not going to be sending out that open message. They will only send out an open message when one of the routers, i.e. R17 in this case, sends that open message. Until then, R19 will not send its open message. When it receives that open message through from R17, it will obviously check the details and the parameters of that open message, and if everything checks out, then it will send across its open message. So think of it like the passive command in OSPF and even in the ISIS world, where you'd configure on any interface here, just using this interface for an example, you would define that to be passive, and then that device wouldn't be sending out any OSPF packets, but it would still then be advertising that interface into that OSPF protocol, into the OSPF world, basically. Similar kind of concept in the BGP world. However, we are going to be sending out those open messages only when an open message has been received, though. So again, that is why we will not be configuring both R17 and R19 to be allowing a particular subnet, because otherwise the adjacency will just never come up. And here I am back on router R19. I'm still within the group external autonomous system number 3, because this is, again, R19 is facing the R17 in autonomous system number 3. And if I just do a quick show, we can see we've got our neighbor addresses. So we're peering to R17, both in peer autonomous system number 3, via two different interfaces. Now what I'm going to do is I'm actually going to delete both of these. So I'm going to delete neighbor 170.22 and .18, and let's do a quick show, and you can see they're now gone. Let's do a commit, and with that now actually committed, if I just do a quick run show BGP summary. So with the run show summary, what we can see is obviously those external connections to R17 are gone. So these are the internal connections, iBGP, to routers R18, R20 and R21, and they're fully established, i.e. they're up basically. Now let's run through that allow command. Just hit the space a few times just to get a little bit of space, of course. Now how do we configure this? Inside the group itself, and I believe you can also do so at the neighbor level and also at the BGP level, but we'll confirm that. Let's do set allow, and if I hit question mark, you can now see I want to open up a set of values itself. So if I hit square brackets and I want to do 170.10.20.20/30, so that is the .21 and .22 network, and hit space, and I also want to include the 170.10.20.16/30, and I also need to now define the peer autonomous system number, so you can't forget that. And now if I do show, you can actually see that we are exporting a particular policy statement. This is type external eBGP. I'm peering to autonomous system number 3, and I'm allowing any IP addresses that fall within this subnet, that fall within this subnet. Now you might be thinking, well, hang on, Dave, that goes against that GTSM part where hackers could spoof an IP packet. Yes, that is true. But what you have to remember here is the subnet size is incredibly small. It's a /30, so you're only going to have 4 IP addresses, 2 of which are actually usable. One is for the network, one is for the broadcast, and 2 are the usable IP addresses. Now one end will have one of those IP addresses, the other end will have the other IP address. So it's not really negating GTSM, you're just allowing a bit more of a flexible approach to allowing BGP and neighbor adjacencies to come up, especially in the data center environment where networks and virtual machines, etc., are constantly changing and adapting. So now if I just do a quick commit check and it's passed, let's run that configuration. And once this has committed, if I then do that run show BGP summary, what we should see is that the adjacencies hopefully being established, but at least trying to get there, because BGP can take a few seconds. So let's do run show BGP summary. And there we go. We can immediately see there is 170.20.18, 170.10.20.22, and they are already established. And you can actually see we've paired to autonomous system number 3. We've had 4 packets coming in on both interfaces. We've sent 7 packets out, fully established, and it was up 3 seconds ago, 7 seconds ago. So that is the allow command. And so there we go, everybody. That is the end of this pretty much short video. It's certainly shorter than other videos I've done on BGP, because at the end of the day, BGP is a humongous protocol. There's so much to learn, and I really hope that you found this video informative and useful. If you did, please give this video a like. It's the best way to support my channel. Additionally, please let me know if you have any comments, questions or queries down in the comments box. I'll be more than happy to answer them. Until the next time, thank you for watching and stay tuned.